Thank you for giving me the opportunity to share my work on popularity bias in recommender systems. So let's get started. Let me go over the agenda first. So I'll be discussing at a very high level what popularity bias is, what are the various sources of popularity bias in recommender systems, why does popularity bias matter, what are the different mitigation strategies and related works that have already been tried out to mitigate this problem. And then I'll deep dive into our proposal of exposure-aware retrieval model, which to handle popularity bias, present some offline and online results that we are getting, and takeaways from our deployment of our solution at scale. So let's dive in, right? What exactly is popularity bias, right? So popularity bias refers to the tendency of the recommender system to over distribute popular items at the expense of less popular ones. So in other words, already popular items get disproportionate exposure while long tail or new items are underrepresented. This is not a unique problem to recommender system, but the dynamic nature of recommender systems actually make this problem much worse, as we will see in later slides, right? So some of the other examples of domains where popularity bias is observed is in academic research, right? Like popular papers just get more citations. Financial markets where popular tickers or stocks are bought more frequently by retail investors. In publishing, for example, right? Like bestseller books are bought more frequently. In hiring, graduates from top or popular colleges get more reach outs, right? So this is not like a phenomena that is only observed in recommender systems. It is sort of a ubiquitous phenomena. But in this talk, I'm going to dive deeper and explore the challenges we have in recommender systems with respect to popularity bias, right? So for recommender systems, let's look at what are the sources we have for popularity bias, right? So primarily, there are three sources of popularity bias. The first is data bias, which means inherently the audience size of the item is imbalanced, right? So some items are naturally more appealing to a broader audience. So even a bias-free algorithm will actually see more interactions on these items, right? The second source of bias is model or algorithmic bias. So this means machine learning models learns patterns from data, and that can include popularity bias. So classic example here is collaborative filtering models, which are built on top of interaction data, and they can reinforce these biases. Even state of the art deep neural networks have big ID embedding tables, which can just memorize the training data and redistribute the popular items which are memorized, right? So the third kind of source of popularity bias is closed feedback loop, which is also known as a system bias, right? So dynamic industry scale recommender systems operate in closed loop, right? Recommendations influence user interactions, which become training data for future models, thereby creating a feedback loop, which can accumulate and exacerbate popularity bias over time. So these are primarily the three main sources of popularity bias. So just to represent them better, so we start off with inherent data collection bias, audience size mismatch, and some items are more resonate more with a larger audience. So right, there is pre-existing or natural bias in the data. Those biases are reflected and reinforced again in when we are learning the model, right? And then our recommender system expose the biased items, right, to the users again, and then the user behavior also has some bias, and this kind of like reinforces and compounds over time in a cyclic manner. So that's a high level kind of like view of how the popularity bias kind of like, gets compounded in a recommender system. So now that we like have a good understanding of like what popularity bias is, like let's discuss why does it really matter, right? So from the user's perspective, right, like there is reduction in novelty and serendipity. Recommendations become like more predictable and less engaging. Um, there is not as deeper personalization. It is the users may not discover items truly aligned with their like niche individual preferences, and there is like decreased user satisfaction and trust in the system, and there is a perception that like the system does not really get me with respect to my niche interests, right? The second is like from the item perspective, right? Like there is a reduced visibility and like maybe sales opportunities for less popular items. There is like unfair competition. Popular items dominate regardless of the quality and relevance to like specific users, for example clickbaits, right? And this could also lead to like item side cold start problem, where new items don't get enough distribution, right? And finally, at a system level, right, like the system behaves suboptimally, catering only to popular items on one side and users who are like, okay with engaging only with popular items, right? So this kind of like setup is suboptimal for the long-term health and growth of the system, because like only a subset of users and a subset of like, items or content creators are kind of deriving the maximum value. Right, so that does not fare well for the long-term health and growth of the system. So let's look at like some of the mitigation goals and strategies that have been tried out in the past to solve this problem, right? So the key goal of these mitigation strategies is to like promote long tail item visibility, improve diversity of interest that we are catering to users, and maintain like overall recommendation accuracy. So we don't want to like digress or like cause drop in user engagement. We want to maintain it and even improve it as much as possible while promoting long tail item visibility and diversity of interest that we are catering to the users, right? So in terms of categorization of like these mitigation strategies, so one is like pre-processing, which means like basically modifying the training data or like sampling strategies before the model training starts itself, right? The second is in processing or in model, which means like integrating the debiasing strategies directly into the model training process. And then finally a post processing where we adjust the recommendation list after the model predictions are obtained, right, during model serving time. So this is like a broad categorization. So now going into our proposal of exposure-aware retrieval model architecture. This is a paper that we have we'll be presenting in UMAP, and we have deployed it at scale. So essentially, how we are trying to address this problem is to cut the feedback loop by reducing the exposure bias that is included in the model training and the recommendation algorithm, right? So we try to correct for this bias and thereby want to kind of like stop this kind of feedback loop that is that gets triggered because of the exposure bias. So diving deeper into it, right? Like what exactly do we mean by exposure-aware retrieval model? So firstly, I would like to acknowledge the work of my colleagues at Meta who have built the accelerator-based retrieval framework. This is a paper that has been published, I think, 12 to 18 months back. So what this does is it enables sophisticated architectures like MTML and mixture of logics to be used in retrieval stage. Unlike the legacy paradigm of kind of like dot product during training and ANN during serving, we can actually use like more kind of advanced MTML and mixture of logics architectures and retrieval, which enable us to do like exposure-aware retrieval modeling. So essentially, what we do is we have a retrieval model which we extend with a parallel exposure prediction head alongside the usual engagement predictions. And at serving time, the model scores are adjusted to account for the exposure. So specifically, like the final retrieval score is computed by subtracting the fraction of the exposure logic from the engagement logic, and we'll discuss more details of it in the following slides. So just to get more understanding of a high level picture, right? So this is a standard kind of like retrieval model where we have like user features, item features, contextual features. We build a multi-objective retrieval model where we have these standard engagement tasks, but we additionally add exposure tasks, which we'll use during training as well as in inference to correct for the popularity or the exposure bias. So now let's look at like how does the training and inference kind of like work in our setting, right? So for the training side, right, like the model that we train jointly optimizes for both engagement and exposure predictions. We use the standard binary cross entropy loss for both the engagement task and the exposure prediction task. We weight the cross entropy loss from the exposure task to make sure that it does not overwhelm the parameters for the engagement task. So we control it by a hyperparameter W, and we do a grid search on it offline, right? And during inference, what we do is we obtain the logics for both the tasks, and we kind of subtract or normalize the exposure logic from the engagement logic to kind of like tune the score of the item at inference time. And the intuition here is like pretty straightforward. Essentially, like subtracting of the logic means kind of like dividing the probabilities. So you can think of it as like we are just like, it's similar to inverse propensity weighting kind of idea, but it's essentially modeling the exposure probability, not kind of like using historical CTR to do inverse propensity weighting. Yeah, that's how we are kind of like training and doing the inference of our model. So let's look at like some of the offline results that we are obtaining. So because this is like a problem related to popularity of items, we need to instrument metrics that can capture the first order effects of our improvements, right? So we instrument two metrics. Positive recall is a pretty standard metric which uses the proportion of truly engaged items retrieved, right? But we additionally instrument another metric, which is a negative recall. It measures the proportion of irrelevant and overpopular items retrieved, but were not engaged by the users, right? So essentially, we want to minimize the negative recall while increasing the positive recall. That's the kind of like trade-off we want to optimize for, right? So as I mentioned, we have the scoring function where we use this kind of like gamma hyperparameter to control the trade-off between how much to weigh the exposure logic, right? So essentially, in offline, we do a grid search of like different values of gamma, and figure out like which value of gamma has the most promising trade-off between the positive and the negative recall, right? And we also use off-policy correction, which is a standard kind of like model proposed by like by YouTube, but that only does bias correction during training time, and we here are proposing doing both in training and in serving time. So we also use that as a baseline to compare our best performing version, and we obtain the best result or best trade-off between positive and negative recall by at gamma equal to 0.65, right? However, I do want to reinforce that like this is still an offline number. We online, what this kind of approach enables us to do is to actually also fine tune the value of gamma when after we have deployed the model and we can do A/B test on it, right? So of course we had done that as well, but I would not like to go into the details of that. But we found the most promising gamma, and then the results that we are obtaining are we can get much more diverse recommendations by doing exposure-aware retrieval, leading to 25% increase in unique items that are being retrieved for users, greatly improving the content diversity. The second is of course, the reduction in popularity dominance. So popular content in recommendations dropped by around 40%. And all of this crucially is obtained without the loss of any overall user engagement, right? So we keep the overall engagement metrics at par, right? So this is the summary of the online results that we got. Sharing some takeaways, right, from this deployment at scale, right? So the exposure-aware scoring provides a tunable mechanism to control popularity bias at inference time. Unlike the one-shot training stage of of policy corrections and inverse propensity weighting, this allows practitioners to adjust the popularity versus engagement trade-offs on the fly to meet various unique business or product goals that we may have, right? Secondly, this allows us to maintain a better trade-off between diversity and engagement. We can get more visibility of niche and long tail content without actually hurting the overall engagement rates, right? It is scalable and production ready. So this solution is actually pretty lightweight. If we are already on GPU accelerators for retrieval model, then it can be deployed pretty easily, right? And it is not specific to any model architectures, not dependent on any model architecture, etc. as well. And also it's domain agnostic. So it has worked well for video recommendations, but we think that it can work well in equally well in other domains. For example, e-commerce, newsfeed recommendations, etc. as well. And yeah, that's all from my side. Any questions? Happy to take those as well.
Thank you so much, Amit. This approach to tackling popularity bias through exposure-aware retrieval is completely new, and it's a really meaningful step to handle this issue. Especially, what struck me is by addressing both during training as well as you implement that during inference time. That's really. So one question I would like to ask is, what trade-off have you observed reducing popularity bias and maintaining the relevance or engagement? I saw the batteries, but if you could explain me.
Yeah, this has been a big challenge, right, to how to balance this trade-off. And we in the past have tried out multiple strategies, right? So for example, inverse propensity weighting or off policy corrections, which are standard training side strategies to improve popularity bias. Sometimes because once you have trained the model, it gets frozen, right? So you don't have as much degrees of freedom. So that's why if we deploy it, we observe regression in kind of engagement metrics. We have no lever going back to training again, which is a very long process, right? So that was a big challenge historically for us. But that's why after these GPU accelerators enabled us to do multitask modeling in retrieval, we could very easily kind of come up with this idea of, hey, let's have a separate exposure task, and then it gives us a lot of degree of freedom to do A/B testing online. And then all of the different products have very different have a lot of online metrics that we care about, right? So by kind of tuning it during online in the online setting, we can observe the trade-offs much better, and then make an informed call about how much to kind of correct for the exposure bias.
That's interesting. So there are two more questions. One is if people are interested in paper and report documentation, and another question: what do you think? How sensitive is the model performance to the gamma hyperparameter?
So regarding the paper, it will be I'll be presenting it in UMAP, which is happening in New York next week, and feel free to connect with me on LinkedIn. Happy to share the preprint version of the paper as well. Yeah, and it will be also available in the ACM proceedings. The second question is how sensitive is the performance for the gamma parameter? Yes, it is sensitive. That is one of the complexity that we are incurring. The good thing is that, like, we have offline simulation where from which, as I discussed, right, like we have the offline simulation and also the metrics instrumented, so we can find, like, okay, what is the rough range of gamma that will work for us, and then when we move to A/B test, we have like a small range over which we need to do a grid search on.
Yeah, thank you so much. So another small question. So how in real time this debiasing helps? Like, really, what are the how you when in production, what improvements did you see?
Yeah. So in production, like going back to our online results, right? We observed that, like, there is substantial reduction in overly popular content, right? So there is a 40% reduction in I can't like go into the details of how we classify popular content because that is like a bit proprietary, but assuming that that's a reasonable definition, we observe a significant reduction in the distribution of popular content, right? And at the same time, like, we observe significant increase in the unique items that can be kind of like, surfaced to the users, right? So from the user's perspective, you can think of it as like, some of the like items which I was interested in are now being shown to me, but previously they were like, we were just like indexing too much on like one or two interests of the users, but now we are able to cover like a broad spectrum of interests of the users, right? So that is that is one way to think about like how users are getting impacted. The other way to think of it is like, let's say you are a content creator and like you are preparing or like uploading content which is very niche, right? That would not be getting as much audience in the previous approaches because like popular items get more distribution. But here, like, as content creators, if you prepare niche content, that also will get more distribution in a personalized manner because we don't observe any user engagement drop, right? So as I discussed, right, in the initial setup, the stakeholders that we had, right, like the three stakeholders that we have: users, item providers, and system, right? All three are observing benefits of it. Yeah.
Thank you so much. This was really interesting talk, especially the recommender system popularity bias as the ongoing problem long time. But this is really very interesting approach. I would like to thank Amit for this interesting talk. And please connect with Amit Jaspal on LinkedIn. And if you have any question, you can ask on Goa app as well after the talk as well. Thank you so much, everyone, for joining.
Thanks a lot for giving me this opportunity to share my work. And yeah, feel free to connect with me on LinkedIn if you want to discuss more about the work that I have presented today. Thank you so much.